Okay. So just a couple of announcements before we get started with the lecture content. Homework 5 is due tonight on Gradescope. And we have an exam coming up next week, Monday, April 5th. I have posted some resources on Piazza about the exam. An exam from spring 2020, its solutions, logistics, all of that. In general, logistics are going to be similar to what we had for exam 1. I did not speed up on YouTube. Okay. Um, so Jerry says the memory stuff was hard. Jerry, please use office hours this week. Have a conversation with me or the TAs. Let's clarify all of that confusion about the memory stuff. Okay. Now, in terms of content, we are going to be looking at lectures 10 to 18. So this is just after what we did on exam 1. So lecture 10 was the control unit, and then 18 will be sort of the last lecture we will have on memory. Okay, so we are going to continue our conversation about memory. This is lecture 4 during the series of lectures on memory. Somebody is unmuted. I would request you guys to mute. I think I got it. The logistic document on Piazza says the exam is 412. Oh, okay. I need to change that. Thank you for catching that. It is April 5th, a Monday. Yeah, that's week. That's next week. Yeah, Monday of next week. So we are 1 week away from the exam. Next Monday. Okay. So what are we talking about today? We are talking about frame allocation and thrashing. Sort of a aggressive term here, but we'll see what that means. So where are frames located? What are frames, and why are we talking about frame allocation? What are frames? You guys know what pages are. What are frames? Frames are page in physical memory, right? So I can say physical pages, right? So these are physical pages. What are pages? Pages are essentially a bunch of contiguous memory blocks, but pages are we refer to that generally with the intention of talking about virtual memory. But when you talk about frame, it is real memory, right? So it is, has some realistic constraints. You have only a physical memory, so it'll have some size limitation. Now the question is, if you have certain processes that need to work on the CPU, how should we allocate the frames that are available to the processor? So that's the reason why we are calling. We are going to talk about frame allocation. And if we don't do this well, then what could happen is thrashing, which essentially means that the CPU doesn't make any progress on the processes, right? So it doesn't execute or do anything useful. So that's the thing that we are talking about today. Let's see. So a quick recap about how does a processor handle a page fault. So there is a CPU over here which is trying to work on this particular load word instruction, for which it has to access the page table. Where is the page table located? Where is this guy? The physical location of the page table. Physical DRAM, that's right. So the page table, when it is in the memory, it is actually in the physical memory, right? Your physical memory, you're calling that your RAM, your main memory, or you're also calling that your physical memory. Yes, DRAM. Now, why is it not cache? Because a page table, when is it in cache, we are going to call that what? A page table in cache, page table, TLB, that's right. A page table, a mini page table, I should say. A mini page table in cache is actually our TLB, translation look aside buffer, right? That's right. So we are going to try to access this page table. Why are we doing this? Why are we accessing the page table at all? I wanted to work on this instruction, so I should directly be trying to read this register from the memory. Why am I looking at the page table? Because I need to find the translation between a virtual memory address and a physical memory address. So I only know the virtual address. CPU is generating a virtual address. I need to find the translation to a physical address using the page table. So I'm going to go look into my RAM to look at that translation. And it looks like, let us assume that this is 0 right now. So let us assume that it starts with a 0. It's not there, right? So the valid bit, when it is 0, that tells you that the translation is not there and the frame address is not present for you to directly look up into the physical memory. Instead, we have a disk address. So if you have a disk address and your valid bit is 0, if your valid bit is 0, what happens? The operating system initiates a what we call a trap addressing error, right? So a trap addressing error. The valid bit is 0. I don't have a physical address. OS, you have a trap addressing error, which goes to the operating system, and operating system in turn initiates a disk IO, right? So it's trying to initiate some disk IO. I'm going to try to access the hard disk, which is slow to read that particular location, right? So I'm going to look at the hard disk, which has all that information, and then bring that frame into the physical memory. When I'm trying to bring that into the physical memory, I may have an empty frame or I may not have an empty frame. So again, we go back and we have to look for about the page replacement algorithms about that, right? But if you have an empty frame, what do? You just bring in the page, and that frame number 2, for example, is going to appear over here. So this disk address is going to go away, and you will now have a frame number. And then now this can go to 1. Right? That's the whole. Now this can go to 1 because now I have the translation between the page number and the frame number. I know it is in frame number 2. And then once you have that, what do? You restart your load word instruction because I now have the information in the page table. I now know where it is located in the physical memory, right? So this is how we handled the page fault. The page fault essentially occurred because the frame number to page number mapping was not available in the page table. So you had to go look into it, the disk, the slow hard disk for that information. But when you looked at it, you also brought it in the physical memory. You also updated the page table in the process. So, and then you have that valid bit becoming a 1 there. Is the access to the disk a slow thing in comparison or a pretty fast operation? Slow. It's extremely slow, right? So it is so slow that the CPU is going to start getting bored, right? Until the page table gets updated, the CPU is thinking, I have nothing to work on, right? Like I really cannot do anything right now. So it is meaningless to leave the CPU unutilized for all that amount of time it spends during that disk read operation. That's your issue. What should the CPU do with itself when a page fault occurs? Because we know, as you guys said, the disk access takes several orders of magnitude longer than the cycle time. It is of the order of an average value of this is 80 million cycles. So about 80 million cycles, the CPU is saying, I don't have anything to work on. So what should you do? Should you simply stall the CPU and not work on any useful program? Or I think it's pretty evident now that you can start working on other programs, right? You could, if one of your programs is page faulting, then your CPU can continue working on that disk IO. During that time, it can start executing other programs or other processes. It can initiate other processes. Now, what would you base this on? Well, because there are several ways to identify that the programs that you can work on. Maybe certain programs are high priority. You could work on that. Certain programs are related to the operating systems. You could work on that. So there are lots of criteria here that the CPU could pick up as, let me work on this particular program. And the idea that multiple programs can share the CPU and the memory is the idea of multitasking, or the degree of multiprogramming. Like we are talking about multiprogramming. How can multiple programs run on the CPU and share the memory together all at once? An active program is called a process. An active program is a process. Now, each process can have different properties of locality. Locality, we know what is locality. Well, it's broken up into two categories. One is temporal locality and the other is spatial locality. In temporal locality, we are looking at memory references that are highly correlated in terms of time. And spatial locality is correlation of memory references that are highly correlated in terms of their address space. So it could be different for different processes, right? Some processes could have a longer correlation in terms of time, but not as much for spatial locality. And some other process could be different in that aspect. Another property of a process is priority. Definitely the operating system related processes will have a higher priority. Another aspect of a process is the size of the process. So for example, some very simple programs, some simple processes may be very small in size, which means that they may not need many frames in the physical memory. But certain other processes might be too large and they might require a lot of frames in the physical memory. So all these are properties of a process which we need to keep track of while we are talking about frame allocation for processes. Now, when a process issues a page fault, let us try to switch the CPU to another process which improves CPU utilization, right? So your goal is not to let the CPU just sit idle. You want it to be working on executing certain processes almost all the time. What are you doing for that? You're just initiating new processes, right? So initiate, your idea over here is initiate new processes to increase CPU utilization. Instead of having nothing else to work on, you're giving the CPU options to work on, okay, process 1, process 2, process 3. Okay, all the 3 processes are page faulting. Okay, now you have another process 4 and 5, right? The more number of processes that you are going to give to the processor, it's going to have more options to work on parallelly, which improves its utilization, right? Think of it as juggling multiple balls together, right? Like juggling of balls. If you have more number of balls, what is going to happen? Well, you're going to have to try to juggle them faster and faster, which means that your hands are kind of working all the time, right? But as you can imagine, if you try to juggle a lot of balls at once, things are not going to go very well. So, and a similar thing happens even in the context of frame allocation. We'll talk about that. Questions so far? How are we doing here? Okay. Now, when you talk about frame allocation, you're trying to look at a few things. One, the total number of frames is limited, right? Physical memory, it's not virtual memory where you can, sort of get an illusion of a big memory. This is talking about physical memory. So, of course, the number of frames are going to be limited. They are going to be finite. And memory is a shared resource between all your programs. Everybody is trying to, there is operating systems, there is process 1, 2, 3. All those things are sort of using this shared number of frames. So we need a smart way to allocate the frames to processes. So what that means is, here you have 4 frames, which is very, not going to happen realistically. You will have a lot more frames than this. But if you had if you say you had process 1 and process 2, on what basis would you assign the 4 frames to process 1 and process 2? Well, somebody might say, I am a supporter of equality and I want frame 0 and frame 1 to be taken up by process 1 and frame 2 and frame 3 to be taken up by process 2. Right? This is what we call equal allocation. All the processes get assigned, get allocated the same number of frames. That's equal allocation. But over here, if you do this is not a realistic scenario, right? Because certain processes might be much bigger in terms of their size than other processes. Then why do we do equal allocation? We don't need to. Certain processes might have higher priority than others. Then equal allocation doesn't make any sense. So that's kind of what we are talking about. How do you allocate frames to processes? How many frames should I allocate to each process that I have, that the CPU is trying to work on? That's the conversation that we are trying to have here. All right. Like I said, these are some basic frame allocation policies. The first one is equal allocation. Same for each process. Very simple, right? That's exactly what we talked about just a moment ago. 4 frames, 2 processes, everybody gets an equal share. So process 1 gets 2 frames, process 2 gets 2 frames. Same for each process. That's equal allocation. It's a simple allocation scheme, but it's not a realistic one because it doesn't make sense for a size. We said there are a lot of properties each process has. Size, we are not taking into account. Priority, we are not taking into account. Locality, we are not taking into account. We are just, the only thing that we are taking into account are 2 things. 1, how many frames do you have? 2, how many processes do you want to work on? That's it. That happens in terms of your equal allocation. The other allocation scheme, which is a little bit more realistic, is proportional allocation, which simply stands for larger allocation for larger processes. And the criteria here is not priority, but it is the size of the process, right? So the bigger the size, the bigger the process. So for example, if in our previous example, if process 1 was bigger, process 1, process 2, if process 1 is bigger than process 2, then we could say, all right, let process 1 take up 3 frames and process 2 gets only 1 frame, right? So that's allocation based on size. It's a proportional allocation. Criteria being size. The third one is even more realistic, which is priority. Larger allocation for higher priority process. So something that is going to be very critical for the CPU, for the operating system, for the computer management. I'm going to give that a bigger allocation in the frames. Now, as you may imagine, sort of the best case scenario is a scheme that is sort of in, taking the advantage of both of these, right? Something that is using the size and the priority as a weighting criteria for allocating frames. Now, when you do this, all of these allocation, you could do this globally or you could do this locally. What that means is, if a particular process needs frames, you could pick those frames that it needs from a global pool, from a pool of frames that is available globally, or a smaller set of frames that was available only for a particular process. So that allocation can happen locally or globally. All right, equal allocation, pretty simple. We have a total number of frames in our physical memory indicated as capital F subtotal. We are counting this after we allocate the frames for the operating system, because that is sort of a non-negotiable deal, right? With the operating system being high priority and quite critical to the existence of the not the existence to work on any other process. We need to have that operating system pages or frames allocated first. So after that allocation, we have cap F subtotal as the total available frames. There are cap P subtotal, number of processes that the CPU could work on, and the allocation per process is simply capital F divided by capital P. Those many number of frames will be allocated to each process. Of course, this needs to be an integer, because you cannot allocate a non-integer number of frames to a process. Now, you may also reserve some free frames in a buffer pool. Why would you need to do this? You got operating system done and you allocated all the other frames equally, but do you think that having some additional free frames in a buffer pool is a good idea? Well, you see, this allocation is not dynamic, right? This allocation is sort of static. You're allocating the frames and that's it. But what if you get some high priority, medium size, high priority process that comes in after you have made that allocation? Well, now you are trying to look for some reserves, right? In that case, you could pick out for those frames from this buffer pool, right? So that's why you have. So think of it like, what you budget in terms of your. Every budget has some miscellaneous expenses, right? Think of it like that. All right. Next allocation scheme is proportional allocation, and the proportionality over here is criteria is what? Criteria is size. Here. Size. Not priority yet, just size. So allocate the frames proportional to the size of the process. So, and suppose we have several processes, P0, P1, P2, P3, Pi, and so on, right? So you have bunch of processes over here indicated by the letters small p and a subscript. The size of any process P sub I is indicated as small s sub I. So small s sub I is the size of that process P sub I. The total process size is going to be the summation of all the sizes of each process. If you sum up all of them, then you get capital S as the total process size. Total number of frames, let us say the same as before, capital F subtotal. So how do you allocate for a process P sub I? You just do allocation for the ith process equals its size divided by the total process size multiplied by the total number of frames that you have available to it. So this is a simple weighting scheme. You're essentially scaling it by the weight of each, the size of each process. And by doing that, you would have allocated the pages to each process. Again, the allocation scheme is based on the size. So a bit more realistic than equal allocation, but still is missing the priority piece. Now, in terms of priority allocation, it is going to be similar to the proportional allocation scheme, but instead of using the size, you use the priority of the process. So the same scheme, right? You're just doing the scaling based on priority as opposed to the size. Now, if a page p sub I during this priority allocation, if a page p sub I generates a page fault, then you can sort of use this to replace. How do you respond to this? You can select for replacement one of its own frames, or what you can do is you can select for replacement of frame from a process with the higher priority. So if one process is page faulting and you're not able to make progress on that, for replacement you could pick one of its own frames, or you could pick a frame from a higher priority. Higher priority is indicated by a lower number. So if in both those criteria, you are sort of bringing in a page that belongs to the same process, or you are bringing in a page or a frame that belongs to a process with higher priority. Now the important question of how many frames to allocate for each active process, and it's kind of critical to kind of highlight this each, right? So we are talking about each active process here, one particular one. There is a maximum number to this, there is a minimum number to this, and if you go lower than the minimum, then you have got to suspend the process. So let us take a look at the maximum, right? Maximum number of frames allocated for each process. How many so if I go back and say this is your physical memory, how many frames can you allocate to each active process? What would be the maximum in this example? 4, right? That's very easy. That is the maximum. And what did you base this on? You base this on the number of available frames in your physical memory, right? That would be the maximum. You have 4 frames over here. That's why the answer to that question would be 4. Let me... There it is, right? So this would be the function of amount of physical memory and page size. That would be your maximum number of frames that you need to allocate for each process. There would also be a minimum. Why minimum? Because now you need to look at the instruction set architecture. Do you have enough frames to process even one instruction function of the instruction set architecture? Those many number of frames would be the minimum. So for example, if you have only one process, P1, and P1 requires 2 frames, for you to make progress on P1, you need 2 frames. If that is the case, the minimum would be 2, right? So to do at least one process function, if you need to have enough, that would set your minimum limit. And if you don't even have that, then you don't have any choice but to suspend the process. You cannot work on it, right? Because you don't have enough frames for that particular process. Now, clearly, you cannot work here, right? Like you cannot be here. Of course, you cannot be here, because then you just suspend. You don't do anything. But you could be here. You could be here. But you could also be here. So where should you be? Should you be here? Should you be close to the maximum? Or should you be somewhere in the middle, right? There is a consequence for each of these choices. Let's talk about what would happen if you operate over here or here, and then there will be a sweet spot. There will be an ideal, just right amount of frames per process. By the way, we all we are discussing right now is a static allocation, right? It's not dynamic, it's not changing. And I suppose you can appreciate that if things were changing, adapting, dynamic, then it would be even more useful. All right. So if you are, say over here, right? So if you are here, what does that mean? That means that per process, you have a lot of them, right? So you have, you know, three, so you have many frames per active process. Well, if you have too many, that is simply a waste, because you could have used the extra frames to run some other process. So if you are going to be over here, then the degree of multiprogramming is going to be low, right? So for example, if I go back to my old example here, way far behind, the maximum number of frames in this guy was 4. Now, if you operate at 3 frames per process, then how many different programs can you work on? Just one, right? Because you will not be able to make progress on the other one. It could be 2 if the other process only needed 1 frame. But I hope you see that the degree of multiprogramming, the number of multiple processes that you can work on in parallel are going to be very low because of that. So you don't want to operate in that region. Over here, it is wasteful because you, and again, this is for each process, right? So for each process, you are way up there, wasteful. A better option is to not be that high and be low so that you can work on other processes. Now, if you are over here, there is a bigger problem, which is called thrashing. You have very few frames per process. What would happen then? Well, if you have very few frames per allocated to each process, then you are going to be page faulting, right? Because now things are not there in the physical memory, which means that you got to go to the hard disk to look them up, to bring them back into the physical memory. You guys see that? So if you have very few frames allocated to each process, then you will be page faulting a lot, which leads to thrashing. Thrashing simply means that you are not making progress on that particular process, right? So too few has a problem of thrashing, too high has a problem of degree of multiprogramming being low. So clearly you want to find a region in the middle here as your ideal number of frames that you want to allocate for a particular process, for every active process, right? So that is thrashing. If a process doesn't have enough pages, it page faults. Its page fault rate consequently goes very high. What is page fault rate? Page fault rate is the ratio. There are two things in here. Number of page faults divided by number of page references. So if you are referencing the page table to look up that information, the denominator is going to sort of increase because those are your number of page references, and the more you need to go to the hard disk to look up information, that's going to increase your number of page faults. So the page fault rate is that particular ratio. Now, if you don't have enough pages, that means that you need to keep swapping things in and out of your physical memory. That would lead to increase in the page fault rate. A process is thrashing if it is spending more time doing this swapping of pages in and out than actually doing something useful and executing the process. That's thrashing for you. And if several processes are thrashing, then the whole system is considered to be thrashing. So it's like you have all these processes that are asking for the CPU attention, but just because the CPU, just because the operating system has to kind of respond to all those trap addressing errors, the time is being spent on responding to the page faults as opposed to working on any of the process. So that's your thrashing. Now, the simple solution to this problem could be, let us try to monitor, or let us try to watch the CPU utilization. And if the CPU utilization is too low, then you can initiate new processes. You see that? So watch the CPU utilization. If it is too low, then you put in more processes. Now, instead of having P1 and P2, increase that to P1, P2, P3, P4, so that now the CPU has more options to work on if there are page faults, thereby increasing the CPU utilization. But this process, this scheme, this solution leads to a vicious cycle. What is that cycle? Let us try to look at it in terms of this diagram here. First, the operating system is monitoring the CPU utilization. If it is very low, if the CPU utilization is very low, it is going to launch more processes. As new processes come in, they are going to need more frames allocated to them. Now, as new processes allocated frames from other processes. Because of that, other processes will start page faulting. Because of that, CPU utilization decreases. And this operating system is going to look at that and then launch more processes. So this cycle is that vicious cycle that is going to keep continuing. So you see, the solutions can work as long as there is a compromise between the thrashing state and the very low degree of multiprogramming state. So let's take a look at that in the graph that is at the bottom here. On the x-axis, we have the degree of multiprogramming. Essentially means the number of processes that the CPU can work on at once. On the y-axis, we have CPU utilization. You want that to be as high as possible. When you have only few programs to work on, then the CPU utilization is low. Why is that? Why is this low? The degree of multiprogramming is low. That means that you only have maybe process 1, or you only have process 1 and 2. And the claim by this graph is that the CPU utilization is very, very low in that case. Why is that? Nothing else to do, not enough processes being run. Okay, nothing for it to do, right? Like that. So the reason is, if processes very small number page fault, we don't have anything else to work on. So CPU is going to just be idle during that time, which is why this is a small number here. So in order to overcome this process, in order to overcome this problem, what do? You increase the number of processes. So as you increase the number of processes, the CPU has more and more options to work on if page faults occur. Even if page faults occur, you go up, you reach a point where you have too many balls to juggle. What happens after that? Well, now that you have a physical limited size physical memory, you have limited physical frames. If your degree of programming becomes too large, what is going to happen? That means that each process is going to get a very, very small number of frames allocated to it, which means that the processes, almost all the processes, will be page faulting all the time, right? So if you get very, very small number of frames allocated to a process, the problem is that you will be thrashing. That's too few frames per active process. See that? So beyond that, the performance drops drastically, because all you're doing here is per process you have got only a few frames, which means to make progress you need to kind of bring in things from the hard disk all the time. You're page faulting all the time. You're not making any progress on the process itself. That is thrashing, and the performance drops dramatically after that. So problem here is small. The degree of multiprogramming is low, right? You cannot be using this for multitasking. Problem here is thrashing. So somewhere over here is where you want to be working at, right? So that would be a good compromise between the degree of multiprogramming and CPU utilization. Those are the two aspects that you want to optimize. And that optimization has to directly do with the number of frames that you allocate to each active process. Whether this is a dynamic allocation or a static allocation. Static allocation, of course, has its problem. Dynamic allocation, we will talk about a specific way we can do this adaptively in the coming few slides. So too few has a problem, too many has a problem. Just right in the middle is what we are trying to aim for. So we could estimate how many frames each process really needs and use this to make allocation decisions. So how do you estimate how many frames a process requires? Well, for that you would need some sort of history, right? Some sort of mechanism to know how many frames did the process need in the past, and based on that, based on certain metrics of past behavior, we can make decisions, allocation decisions for the future. But we cannot be doing this far out in time. We cannot take the estimate based on history that was sort of way far in the past. Why is that? Because there is temporal locality, right? Everything is going to be correlated in terms of time. So we need to estimate now and then make that allocation, and then keep doing this for in a continuous manner. So we are going to talk about the property of the process that we are going to try to leverage to find out the number of frames we need to allocate for a particular process, and that is locality. We are going to try to leverage the locality aspect of the process. And again, locality is divided into two types of locality, right? One is temporal locality, which means based on time. The other one is spatial locality, which means in the correlation in the memory address space. So the red, this chart we have seen before. These are memory accesses, memory address accesses for a particular memory reference pattern. X-axis is the execution time, Y-axis is your memory addresses. So X-axis time, Y-axis addresses, which means space, right? So you can think of it as time and space axis. Each dot refers to a memory reference, memory access. So we can see that in terms of temporal locality, temporal is time, right? So you can see that these dots are bunched together in the horizontal direction. There's a high correlation. So things that are referenced, they are referenced again and again in a tight time window. So that's correlation, a high correlation of memory accesses in terms of the x direction. So that's temporal locality bunch along the x-axis. And there is also a temporal locality based on locality based on the y-axis, which is the spatial locality. So that's bunching along the y-axis. So these two metrics can tell you a good number of a reasonable number of frames we need to allocate for processes. But we still, after having leveraged locality, we still could have a thrashing problem. And the reason for that is the total size of locality would still be more than the allocated memory size. So for example, if the total size of the memory, right, like we have looked at its locality chart, and based on the locality, we have come to a conclusion that we need to allocate 5 frames to a process, right? But if that is greater than what we have really allocated to that process, say 4, right? We have only allocated 4 frames to it. We have allocated only 4, but we need 5. That means that again we will be page faulting. Again, we will have the same problem because we need 5, we have only allocated 4. So we still could have the problem of thrashing, which is why we can go to a working set model. So something that can estimate the number of frames based on a dynamic estimation, something that can be changing, right? So a working set is what? The set of frames that a process is actively referencing. Again, this is going to be for a specific duration of time. So for a specific duration of time, if a process is referencing a set of frames, then it is called that working set. So for example, let's see, if I go back and look at this, right? If process 1 references frame 0, frame 1, frame 2, frame 0, frame 1, frame 2, these 3 frames for a specific duration of time, then those 3 frames would make up the working set for that particular active process. So that's your working set. What we are going to do is allocate enough frames to satisfy the current working set. So if the working set is, say, 3 unique frames, and we allocate 3 frames to that process, we are going to be good, because we know that this particular process is continuously referencing only 3 unique frames, and we have allocated 3 frames to it. That is sufficient. We are going to be okay. If there are enough extra free frames, what can we do? We can increase the degree of multiprogramming. Every time you have a low CPU utilization and you want to increase that, all you need to do is launch new processes. And in this case, we are trying to take advantage of any extra free frames that we could have after we allocate the frames, enough frames to satisfy the current working set. Next, if the sum of the working set sizes for all the active process exceed your number of frames that are available, you have to track things back. You have to decrease the degree of multiprogramming, which essentially means suspending one or more processes, right? Processes. There is a very nice example about this, which sort of brings everything together on the next slide. But before we look at that numerical example, let us define a few parameters that we are going to reference over there. Delta first is the working set window. So this is how many page references are you talking about, right? How many page references are you going to be looking at to talk about this working set? Is that going to be the last 3 page references, last 10 page references? So that's going to be your delta, working set window. Then there is WSS sub I, that is the size of the working set for process P sub I. This is the total number of unique pages referenced in the most recent delta references. If the working set window is too small, what would that make it? Well, it will not encompass entire locality, right? So essentially you're saying that I'm only going to include the last 2 page references into my calculation. Well, last 2 references is just a little bit of history, not total amount of history that you could really take advantage of, right? So delta is too small is not going to give you a very good idea about the good allocation of the frames because you're not really leveraging locality in that case. If delta is too large, then we are kind of going over multiple localities, right? Not just one of them. Then we are going to be looking at a lot of time. Then if you're looking at a lot of time, then you're kind of going over multiple localities. You don't want to do that either. And delta definitely cannot be infinity because that would encompass the entire program. Then it's not going to be meaningful at all. What is D? D is the total number of working set, the total number of demand frames. So how many frames are you demanding for all your processes combined? If you sum up all the working set sizes, that would give you capital D. If capital D is greater than the total number of available frames, then that would lead to thrashing. And the way to come out of thrashing is to suspend one process. Take a look. If you're still thrashing, suspend one more process, and so on. Now let's take a look at this working set estimation using this particular example. Now this example is going to be interesting. I recommend that you pay full attention here. We are starting off with some arbitrary delta, right? So our working set window here is 10 page references. So this is 10 page references. Number of page references. So what we are doing is we are doing this estimation at 2 times. One is at T1. So let me highlight T1 right here. That's at T1. And the other is at T1 plus some other arbitrary time T. Now, what are you looking at? You're looking at the last 10 page references. By the way, what is this? This is a page reference string, right? Something very similar to the page referencing string that you saw in the last class when we were talking about the page replacement algorithms. It is the same thing over here. So page 4, 2, 6 is being referenced, right? So at T1, if you look at the last 10 page references, what do you have? You have the working set as a function of T1. How many unique page references do you see over there? You see a 1, you see a 2, you see a 5, you see a 6, you see a 7, right? 7 you see multiple times. But the total number of unique page references is going to be 1, 2, 3, 4, 5. 5 is your working set size as a function of T1. So that's 5. Let's move to another time. T1 plus cap T, that's your T2. Right, so this is T2. At T2, if you still look at the last 10 page references, what do you have? You only have 3 and 4, right? So the working set at as a function of T2 is 3 and 4 as the unique page references, and the size of this is 3 and 4, 1 and 2. So 2. You see that? So what does this tell you? Working set size at T2 is 2. Working set size as a function of T1 is 5. So based on this, what are we trying to answer? Frame allocation, right? So how many frames would you allocate to this process? Number of frames allocated equals. How many frames would you allocate here? If you had a choice Oh, no. 7 is your best case scenario. 7 is like saying all of them to one process, right? You That's a little bit too much. You don't want to give uh, more than what you need. 5. Okay, so we are getting closer, right? So if I did 5, you see, I would be pretty okay during this time window, right? No page faults during here, right? Because all of that is already there. And then as I move here, I get some page faults, but after that I'm fine because I have 5 frames allocated to this process, but I'm only referencing 2 of them over here. So I'm going to be pretty solid, no page faults during that time. I'm not going to be thrashing this process during that time. Of course, 7 is also an acceptable answer, but then all the page references are for that 1 through 7 pages. So if we allocate all of the available frames to that process, then it's not serving you any purpose. You cannot increase your degree of multiprogramming by doing that. If you have 5, then you are going to be pretty okay over here. There are a few pages here. Say 6 is not included in this, 2 is not included in this, 1 is not included in this, which means that if you were 5, you would be okay all throughout. You see that? Because the unique pages that are being referenced is 5 here, is 2 here. By using that, you can allocate the number of frames to this particular process as 5. And you can keep changing this as well. You can have a particular number here, you can make it low here, you can make it high here. So you can dynamically change the number of frames allocated to this process by essentially monitoring the last 10 page references or the last 15 page references. You see that? So by doing that, your goal is to keep adapting to the page reference string. Your goal being 2 things. CPU utilization should be high and the degree of multiprogramming should be high. Now, let me ask you 2 things here. What would happen if I made delta too big? Delta is too big, right? What would be the problem if I made delta too big? So instead of 10, what if I made this 100? Would I be able to use this working set size estimation if I made that 100? Would that give me, would there be any use of doing that? No, right? Because if I make this 100, then I'm looking at the last 100 page references. And of course, if you look at the last 100 page references, that process would have referenced each page, right? Then you might as well just say, all right, how many frames you have available? Just allocate all of them to this process, right? Then there's no point of doing this working set size estimation. So too big, not helpful at all. And you are kind of going over multiple localities by doing that, right? Delta too small, is that going to be okay? Good, bad? So right now it is 10. What happens if you do 1 or 2? Is that going to be good? Essentially, you're trying to. The question is this: in order to come up with the number of frames allocated to this process, should I look at the last 2 page references? Is that going to be enough to estimate the number of frames? That's too low, right? So if you're looking at just the last 2, then your estimation, which is based on history, is taking into account things that happened in the recent history, right? Just 1 and 5, just 1, 5 and 7. So that is not going to give you a good assessment about how many total number of frames you can allocate, because that is not even total, the entire locality. It should encompass some locality, right? So a good way of picking delta is to go back and take a look at your locality chart and say, all right, maybe 10 is enough, right? So that's where you would get that number from. Next, how about this T1 and T2? Would this make sense if you did this T1 and then this T2, and you suppose you kept it at 5 at both places? What would be the consequence if you made this estimation too far out, which essentially means that T1 is much smaller than T2? If T1 is much smaller than T2, then that page reference calculation or your working set size estimation is based on events that happened very far out in history, right? So that doesn't give you any correlation data in terms of its temporal locality. So you don't want this T to be too big, and you also don't want this T to be too small. If it is too small, what would happen? These page references, the blue and the red, would sort of overlap, right? So if they overlap, then it's not giving you a good estimation of the number of frames. The localities are going to be overlapping. So it cannot be too far out, it cannot be too close in. Delta also cannot be too big or cannot be too small. So when you do this working set estimation, you need to pick a suitable choice for delta as well as for T, so that you can get a reasonable estimate of true set size. Usually this is done through experimentation. So run some real processes on a CPU, experiment with it, see how your working sets to essentially figure out that delta and T, the separation in time. And then if you need to tune it using the system manager. All right. Questions about this? Do you see how we are using locality as leveraging locality to find a working set size, and you're using that working set size to give you an assessment about the total number of frames you need to allocate for that particular process. And by doing that, you can also change it dynamically as time goes on. Okay. All right. Another approach to avoid thrashing is to monitor the page fault frequency. So take a look at this graph here. On the y-axis, you have page fault rate. Essentially is what? Page faults, number of page faults divided by the number of page references. That's your y-axis. On the x-axis, you have the number of frames. If you have very small number of frames per process, of course your page fault rate is going to be too high, right? So page fault number of frames, say you have only 1 or 2 or 3, very small number of frames per process. This is for each process. If they are too small, then you are going to need to look up information in the disk many times. That would increase your page fault rate because of that. Now, if you want to decrease the page fault rate, what can you do? You can increase the number of frames, right? So if you increase the number of frames per process, then you do not have a high page fault rate. Now you may have enough number of frames for that process to execute. So the page fault rate goes down because of that. And it keeps going down as you keep increasing the number of frames for that particular process. However, if you increase the number of frames per process to a big number, you have another problem. What is that? What is this problem? What is the problem here? The number of frames per process is too high. What happens because of that? How many will each process get? A small number, a big number? You're trying to monitor the page fault rate. How many page faults are you getting? Number of page faults divided by number of page references. In the last 10 page references, you got 2 page faults. The page fault rate is 20%. If you start off with number of frames, this is per process. If your number of frames per process is very, very small, then your page fault rate is going to be too high. Do you guys agree with that? All right. So if the number of frames per process is small, your page fault rate is too big because you do not have enough frames for that process to make progress. You have to keep on looking up information in the hard disk because you have allocated very, very small number of frames for that process. The only way to reduce page fault rate in that scenario is to increase the number of frames for that process. Instead of 4 frames, go to 10 frames for that process. Go to 15 frames for that process. As you increase the number of frames for that process, its page fault rate is going to go down because I don't need to look up the hard disk for that. I already have it in the physical memory because I have the number of frames. I have frames for it. So that is going to go down. But if I go down too much, I have another problem. What is the problem over there? Here, the number of frames per process is too high. What is the problem there? Number of frames per process is too high. What is the problem there? Low CPU utilization. I wouldn't call low CPU utilization. I won't call it low CPU. I would call it degree of multiprogramming is low. Is low. Can't run enough processes. So if you have 15 frames for this process, 20 frames, 100 frames for this process, because you have a limitation on the number of frames in the physical memory, you can only have maybe 2 processes, 3 processes, right? So the degree of multiprogramming in that case will be low. You will not be able to do too many programs in parallel because of that. So there is a lower bound to this, right? There is a lower bound to this. Beyond that, your degree of multiprogramming is too low. If your number of frames are too low, the problem is that you are thrashing. If the number of frames are too high, the problem is that your degree of multiprogramming is too low. So there is a sweet spot that you can operate in by observing the page fault rate. If it is too high, increase the number of frames. If it becomes if the degree of multiprogramming becomes too low, then you decrease the number of frames per that process and you come up in this white region here between the lower and upper bound. All you're doing is you are monitoring the page fault rate, and you are uh, you know trying to be between these two bounds by monitoring the page fault rate. So let me ask you this: what do you do? What do you do when the page fault rate is too low? What should this? What do you do when page fault rate is too high? What should you do? Lower number of processes. No. This is per process. Increase number of frames, right? Increase number of frames. This chart is per process. So you increase the number of frames. If you are here, then you increase the number of frames. You go down. If you go down, you have a problem of degree of the number of programs you can execute in parallel are very small. And to fix that, what do you need to do? Do you need to decrease the number of frames, right? So the solution is right here: increase or decrease the number of frames, right? All right. Let us summarize our paging issues. So this is sort of what we have been talking about in the last few lectures. One, when should a page be brought into memory? Let me ask you this: when should you bring a page into memory, physical memory? When should you bring it? When should a page be brought into memory? When it is not in the memory, when it is referenced. Okay, when it is referenced and it is not in the memory, right? What do we call that? A miss. Okay. Cache miss. No, there's no cache here in the memory, as in main memory, a RAM. So a page fault. That's right. So when we have a page fault, that's when we will bring a page from hard disk to memory. Which page gets replaced when a new page is brought in? We talked about the page replacement algorithms. There was a first in, first out, pretty simple, but has a pretty high page fault rate. Then there was an optimal algorithm, which was essentially used for benchmarking. And there was a least recently used, also called as the least frequently used algorithm. Right? That was for when you try to bring a new page, which should you replace? And then the topics for today included: how many frames should you allocate for each process? Should you do equal? Maybe not. Very simplistic, unrealistic. Proportional, based on what? Based on size, based on priority. Those are a combination of size and priority would be a pretty good option. And then we looked at a working set model in which we were looking at the number of unique pages being referenced in a given amount of history, right? Like in a given amount of fixed page references in the past. And by looking at that, we could leverage locality and come up with a suitable number of frames to be allocated for that process. We also didn't want this estimation to be too far out, right? In terms of estimation, we also didn't want it to be too close. So there were two parameters that we played with: delta and small t. And another approach to reducing the thrashing was to monitor the page fault frequency. If it is too high, then you increase the number of frames for a process. If the page fault rate becomes too low, then it indicates that your degree of multiprogramming has also become too low, and the way to get around that is to decrease the number of frames for each process, for that process. All right. you guys are all ready for the activity. I'm going to be here. Please get started on that. I'm going to stop recording here.